in all our optimization examples up to here, we ended up with, so sometimes we had to find them ourselves, an explicit formula for the relationship between what we wanted, time or cost, and the variables we could control. Sometimes, though, especially in biology and economics, we don't really have exact formulas. We have rough shapes of graphs, but not formulas themselves. So how do we go about tackling those kinds of problems? There's one important class that we're going to study here through a particular example. So I'd like you to imagine a chipmunk. Chipmunks are small little rodents that carry food back to a nest to store it for wintertime. Now, this is called foraging, and they have a slight challenge when they do this, though. They can only put so much food in their face, for lack of a better way to put it. They do not have pockets or knapsacks, so when they go out to forage for food, there's a limit to how much they can bring back each trip. So if you imagine stuffing your own face full of peanuts or crackers, you can imagine that your mouth gets full after a certain amount of time. And this would show up on a graph as the amount of food gathered versus time. What I want to emphasize here is this is for one trip out of the nest. So if there's some time that it takes for us to leave the nest and get to the foraging site, this might also include the return trip for reference, and then we start foraging, well, we can put food in really quickly and get our mouth mostly full pretty fast. If we spend longer on it, though, we get the idea of diminishing returns, where we get less benefit for each amount of time spent. So here's a graph that represents something to do with what we want to optimize, but it's actually not entirely what we want to optimize here, because it's pretty clear from this graph, the longer we spend foraging on our one trip, the more food we'll get, but somehow we feel that it's not as efficient to keep doing that as it would be to do something else. Okay, let's see how we can break this down. This graph is capital F of t. It's the amount of food collected in time t. There's also a travel time. This is tau, for those who have not seen it before, the Greek letter tau. And we have a total trip time then of t plus tau. What are we interested in if we're a species? If we're a species of chipmunk, what's going to make us survive better? It's not going to be the amount per trip. I don't really care how much I get per trip. What we want to optimize is the efficiency, which is amount per unit time. I can take more trips if I take shorter trips. So what I really want to optimize overall is, in a given day, how much food can I gather? The total amount of food gathered per unit time will be a measure of that. So how do we optimize that? Well, we first have to define it. Well, it's amount of food gathered per unit time, R of t, is amount gathered per time spent. And we just said that the F graph gave us the amount gathered, and we just said that we would take t time gathering, plus that tau value, which is how long we had to travel for. That ratio is our efficiency, or our average collection rate over time, average collection rate per unit time. So this is what we want to optimize. And then we can start seeing the trade-offs we mentioned in the graph. If I'm willing to spend more time, I will definitely get more food, but I'm going to be dividing by that extra time when I look at how it affects my efficiency. And so there will be a trade-off between more food for more time, and it's shown in this ratio here. How do we see this on the graph, though? If we talk about R of t being F of t over t plus tau is the more traditional way to write it, so we'll do that here. If we look at this, this is exactly a rise over run scenario. f of t from 0. Let's pick a point over here, say. If that's t, then this distance is also t is either a point or an interval, and this is tau. Then going from 0f up to f of t, that's there, and we divide by the run t plus tau, we're going to get the straight line joining here to here. This is f of t, this interval here is t plus tau, and so r of t is represented by the slope of this line that we just drew. If we pick a different t value, let's do one in red, if we picked another t value here, so that was our t interval, we go up the graph here, we would take the same anchor on the left, go up to our graph, try to make it straighter than that. There we go. This slope of this line would be our rate of gathering. And we can see that as we pick different points on the graph or different gathering times, we get different slopes, and our goal to maximize r of t is synonymous on the graph here with maximizing the slope of those lines. Slope of line connecting the start point with f of t. That slope will tell us how much food we've gathered over a unit time, and we can see that this red line has a steeper slope. That's where we get the payoff for being more efficient at the beginning. By following the blue line, we spent all this extra time gathering food, but only this much more extra food for this much longer time interval. That's less efficient. Picking this dot on the red line would be a better choice for overall efficiency. All right. What can we do to follow up on this? How can we get to some kind of important formula? What if we don't know the function f of t? Well, but we just know the basic shape. Well, we know that r of t is f of t over t plus this travel time constant tau. Important to recognize that this is a constant. If we wanted to optimize r with formulas, then what do? Well, we'd set r prime equal to 0. We'd look for critical points. Well, what's r prime going to equal? This is going to be a quotient, so we take the derivative of the top times the bottom minus the top times the derivative of the bottom, but that's just 1, so that's okay, all over the bottom squared. All right, so if you want the derivative, we would compute it based on this ratio, which defines our food gathered per unit time. Then we'd set it equal to 0, set that derivative equal to 0, and let's just write it out again. Over t plus tau squared. Now t plus tau will never be 0, so we can actually get rid of that because we can multiply both sides through. I'm going to bring the f of t over, and f prime of t, t plus tau. Now it's not clear what we want to solve for here, but if I do something and divide through by t plus tau here, I think you'll see what we just did. This is familiar. In fact, this is exactly r of t. R of t. And on the right-hand side, we have a derivative of f. Remember what we wanted here. We wanted to optimize r, so we were looking at r prime. But now we found a condition that when r prime equals 0, which is likely a max, could be possibly a min, but likely a max in our scenario here, r of t equals f prime of t. we're going to go to the next page here and see if you can think about what that means in the context of a graph of f. So take a look at this point, all these points here, and ask yourself, which of the following points maximizes the value of r of t? And we just said r prime equals 0 when r of t equals f prime of t. So think about that for a second, and then we'll go and look at it. Okay, r of t is the slope of the line connecting here to a point on the graph. F prime of t is the instantaneous slope, instantaneous slope, or the tangent slope of f. This is the slope of line representing the average rate. So if we look at all the possible slopes here, going to A, then going to B, then going to C, one of these, B in particular here, I'm going to erase the others, the line connecting B back to that starting point is the one that's steepest. That's when we get a maximum R. The maximum R happens here, and it's also when it's just tangent, when this average line is just tangent to the curve, or when the slope of the line representing the average rate has the same slope as the tangent line slope. For comparison, let's do an extreme example here with E, with hopefully a better straight line interpretation. There we go. At the point E, this line and this line are not the same. Our condition said they have to be the same if we're looking for the optimal rate of accumulation here. At the point B, those two slopes are the same. The tangent line and the straight line are the same. The average rate slope are the same. And so we do get a maximum harvesting rate. Now, this is not just one example either. This idea that the optimal time to stop harvesting occurs when the current average rate, r of t, equals the current instantaneous rate, f prime of t, that's something called the marginal value theorem. It shows up in economics, it shows up in finance, it shows up in biology, especially in evolutionary biology, where we look at these kinds of efficiency measures. And you'll notice it's going to be a property that's true regardless of what the actual formula for f of t is. We didn't need to know it. As long as it has something roughly this shape, there's going to be one optimal point that we can identify based on this criteria, that the average rate is equal to the instantaneous rate of change at the optimum. We'll see some problems like that in your assignment.